Hi there, Jeff Rideout from Memorial University with the final video in a very introductory series on Matlab. This video will deal with Simulink, which is a Matlab add-in, I suppose. It lets you use block diagrams to symbolically represent systems instead of using computer code. Referring to the projectile problem that we did earlier in an earlier video, basic high school physics, projectile motion, acceleration is constant, and you can solve for the equations for the position and the velocity, and we coded those in an earlier video. Scrolling down to page 11 of the document, suppose we want to increase the realism of this by saying that we're going to put an aerodynamic drag force in. So if the mass is moving upward with some velocity v, there's going to be an opposing drag force which will be equal to some constant times velocity squared. And gravity will be acting down on the particle. If we do a free body diagram of the mass in midair, if we do some of the forces downward equals ma, if we do some of the forces upward equals ma, let's see, the forces upward are minus cv squared, but we represent that as c times v times the absolute velocity of v, because if you have cv squared, v squared is always positive. We want cv squared to be positive when the mass is moving in one direction, and when the mass is moving in the other direction, the drag force should flip its direction, so we should see a flip in the algebraic sign. CV, absolute value of v, gives you the magnitude cv squared, but the sign of this term will change if the velocity goes from positive to negative. Okay, so we have minus cv absolute value of v as a downward drag force, which is negative upward. We have minus mg upward, or mg downward. So the sum of those upward forces would equal ma. If we solve for the acceleration, we see it's no longer simply minus 9.81. It is a function of g, and it is a function of the velocity. Okay, the more velocity, the more drag force, and the acceleration will change accordingly. This is an example of a computer simulation problem where we have the acceleration, and we have the initial position and velocity. We need to calculate new positions and new velocities, update the acceleration, and then repeat. So we're going to do that with the aid of the Simulink add-in. We're going to use the parameters shown on the screen, which we used before. All right. The equation we have here, its acceleration is a function of mg, c, and v. I can split that equation into two first-order differential equations. I can say that y dot equals v. Okay, so the velocity is the derivative of the position with respect to time. So the over dot here is basically saying dy by dt. So dy by dt, rate of change of position, is velocity. Acceleration is the rate of change of velocity. So v dot, or dv by dt, equals the acceleration, as shown in the equation on page 11. So v dot is minus 1 over m, mg plus cv, absolute value of v. You can numerically integrate these equations, and by numerically integrate I mean take y dot and v dot and integrate them to get y and v. You can do that in code using Matlab's ODE function. But for now, let's do this in a more, let's say, visual, graphical way using Simulink. Alright, so to start Simulink, I'm going to follow this document. You may find it handy to have in front of you. I'm going to switch over now to the Matlab command window, and I'm going to type Simulink, and it is going to open up a new environment. I'm going to create a blank model, and it's just a blank workspace. I'm going to pull elements in from the Simulink library. So I see now I have a library tab opened. Depending on the toolboxes you have, there's many neat things you can do. I'm going to go with the standard Simulink library. I'm going to start dragging in blocks. So there's a list on the in the document of what you're going to need. I'm going to go into commonly used blocks. I'm going to need a constant block. I am going to need a gain block which multiplies things by a certain gain or number. I will need a summation block to add or subtract various signals. Bring these in the orientation that I will have them in at the end. If I want another gain block, I can bring another one in from the library, or I can select it and I can Control-C, Control-V to cut and paste. And let me paste another one. And I'm going to need a product block. If you want to keep track of time in Simulink, you can actually bring in a clock which will spit out the time. And that's in the Sources sublibrary. Right, so under Sources, I can bring in a clock. What else do I want? I know there's absolute value in my expression for acceleration. Not seeing that one in the commonly used blocks. Now, absolute value is a nonlinear thing, so I'll go into, let's try discontinuity, see if it's in there. Okay, it's not in there. Math operations, maybe? Absolute value, there it is. It's worth your while to poke around these libraries and just get familiar with all the different blocks that are available. I mentioned how we're going to integrate acceleration to get velocity, and we're going to integrate velocity to get position, so we can plot position and velocity with our nonlinear, non-constant acceleration. The integration is going to be done with integrator blocks. Those are in the commonly used blocks library. They're also in other places. We're going to do two integrations. I'm going to bring in two integrator blocks. The integrator blocks have a 1 over S in them. If you've done a controls course and you're familiar with Bode plots in the S domain, you'll recognize 1 over S as a Laplace domain integration. So it doesn't have the nice little curly integral symbol you may be used to. And that's okay. Now, let us begin. This is one of those things where when you see this done the first time, it may click and you'll say, oh, that's really neat. I'm going to take, let's see, I'm going to join one of these gain blocks to the first integrator block, and I'm going to join the first integrator block to the second integrator block. Okay, so I'm going to use all these elements here to cobble together the acceleration. I'm going to double click on this signal, and it's going to open up a place where I can type in a label. I'm going to put in A. So whatever this signal is, it's going to be the acceleration. Now, whatever the acceleration is, when I integrate it, I'm going to end up with velocity. And coming out the other side of this thing, I'm going to have displacement. I need to connect this to somewhere for now, so I'm going to bring in a thing called a terminator block. And as you can probably tell, the connection is pretty simple. You hover over the connection port, your cursor becomes a cross, you drag it over to the connection port of the adjacent element, and it connects it pretty seamlessly. Double click on this. Now this is going to be the position Y. So this is sort of the heart of our little numerical integration operation here. With my mouse wheel, if I scroll the mouse wheel, I can zoom in. Okay, so we're going to have an acceleration signal. We're going to integrate it to get velocity. We're going to integrate it again to get the displacement. In these integrator blocks, if I double click on them, I get a little dialog box here. Most of these things you can leave alone. You can set the initial condition, though. If we want to use an initial velocity of 5, I would set that as an initial condition in the integrator block parameters. If we want the initial position to be 100 meters, I will double click on the integrator block. That will give me position, and then that one will, I'll set that initial condition to 100. All right. So now all that's required is to put together the acceleration signal. Now the acceleration, the expression for it was, what was the acceleration? The acceleration was minus 1 over the mass times mg plus cv, absolute value of v. All right, so I think the first thing I'll do is I'll do v times the absolute value of v. So I got this absolute value block hanging around. I'm going to flip it. I'm going to right-click on it. Now with my screen recorder, it's not easy to do this. I may have to cursor on it a few times, but if you right-click on the block, you should see Format Block, and then you should be able to flip the block, or orient it however you want. To get the absolute value of v, I start at this absolute value block, I pull the signal down, I'm clicking and dragging, and if I go into the v and let go, it'll put a little node in there. So now it's just extracting v and taking the absolute value. If I want to multiply the absolute value of v times v, let me just try to flip this block as well. That block, flip block. Okay, I'm going to take the absolute value of v and connect it there. And then I'm going to multiply it by simply v. So I'll just drag it down to the velocity signal, not going through the absolute value block. And you can see it does a good job of formatting those little arrows to make them look neat. So now I have v times absolute value of v. I have to multiply that by the c parameter, which in the handout is going to be 0.01. So that'll be a gain type of situation. So format, I will flip this block just to make it look good. I will double click on this gain block and set the gain to 0.05. I can also click on this gain 2, double click on that, and I can put in c so that I know that this is the c parameter. You can see that I've just got a k in there instead of the number I just put in. If I expand this to give it enough room to display the 0.05, then I'll see that quite clearly. Now I have CV, absolute value of v. That was one of the terms in my acceleration expression. The other one was mg. Now I'll do mg. I'll take this constant block, I'll double click, I'll make it a 9.81. And I can double click on the constant label and make that lowercase g. mg, well, the mass was 2, so I'll put in a mass of 2 there. I can, again, label that mass. I can bring this down, I can connect. Now I've got mg. All right. To get the acceleration expression, if I take mg and add it to cv, absolute value of v, and then multiply it by minus 1 over the mass, then I get the acceleration expression. So I will add, using this summation block, I will add mg and cv, absolute value of v, and then I'll take the output of this and I'll multiply it by minus 1 over the mass. Now by right-clicking on this, I can change the location of these pluses, and I can change the output of the power port to make it look a little better. I'm going to take my summation of mg and cv, absolute value of v, and I'm going to pull it right into this gain block. And this gain block is going to be minus 1 over m. Now the mass was 2, so I will make minus 1 over m equal to minus 0.5. Okay, and now I've got a complete system. So at this point I can stop and say, hey, whatever v is at the current time, I can use that along with mg and these other gains to make an acceleration signal, which I can integrate twice and get the velocity y, sorry, get the position y. If I want to look at this, plot a graph of it, there's two things I can do. I can go into what are called sinks. Sinks are places where signals go to be used or just terminated. There's a scope here. I can pull that in. I can then left click on the connection port, drag the signal down, and now this scope will give me a plot of y. And I can copy and paste that, and I can take a look at the velocity as well if I want. All right, and I can call that v. The other thing I can do is if I want to plot these things in Matlab's Workspace, under the sinks I can go to Workspace. Now I'll connect that into here. So I want to take the y variable and I want to go out to the workspace. Maybe I want to do the same thing for the time. So I'll have another sim out block to go to for the time. If I double click on this, I can give it a variable name. I can call it time. I want to save the format as an array. I want to plot a big vector of values. This one I'll call the variable name y. I'll again save it as an array. Alright, so when I run this, there's one other thing I have to do. Simulink has a number of elegant variable structures which have certain advantages. If I want my data to simply be in an array in Matlab's Workspace, I have to go into this Prepare menu, select the drop-down, Configure Logging. If I want just a regular old array, I need to unclick the signal logging data stores and single simulation output and only have the time and the output variables saved to the workspace. And I want to have them in the format of an array. So if you don't make these changes, you may see an unusual looking variable appearing in Matlab's Workspace that's difficult to plot. Alright, to run, I simply hit run. Now what are my options down here? I can run, I can slow down the simulation. I'll just run it. On the bottom of the screen, there's a numerical integrator scheme that you can click on. Right now it uses variable step auto. We don't need to get into that right now, but there are a number of solvers that you can use to do the numerical simulation. The default one will work in most scenarios that you'll encounter early on in your simulation career. So I'm simply going to run this. It has to compile, and then it does the numerical integration. This runs quite quickly. If I now go into the Matlab Workspace and type whos, I can see that I have t out and I have y. So I can plot those with my plot command. Plot t out and y. They have the same size, so there will be no problem there. And here I see the position starting at 100. It had an initial upward velocity, so it goes up a little bit, levels off, and then comes back down. And I can format my axes as per the plot command and other related commands in an earlier video. If I want to stay within Simulink, I can double-click on the scope, and it'll open up the graph for me. So you can put a scope in anywhere to keep an eye on a signal. Here's the velocity, and you can see that the slope of the velocity is not constant. In the regular projectile problem with no aerodynamic drag, acceleration is always minus 9.81, which means the slope of this line would be constant minus 9.81. When the velocity gets really big, like someone jumping out of an airplane, eventually you reach terminal velocity. There comes a point where the mass is falling at such a speed that mg is balanced out by the drag force, and then you see that the velocity eventually becomes constant. So terminal velocity here is minus 20. Anyway, we're digressing a little bit. The main thing is that with the Simulink library, you can drop and drag elements in, you can modify them, you can format them, and you can do very easy numerical integration. So this is legit computer simulation. Okay. So that concludes this series of introductory videos to MATLAB commands, MATLAB programming, and the use of Simulink for simulation. Thank you.